real key area is quantum mechanics and how it defines the properties of materials and stuff like that, and so you need integration for that. But we're not going to start there, so let's just start with the mathematical framework. All right. So let's give ourselves some function to integrate. And f of x. Now we'll remove that after a while, but so need the math library, but for now just x times x times x minus 1, and okay, float a b and then we'll print integral from a to b of f equals a b integral. Right, we have to get that integral. So for that problem, we're going to approximate the integral, which is the computation of the area. The usual way we do it in mathematics is we slice up the interval into really small intervals, and then we make rectangles, for instance, in these smaller intervals, and we adjust the height of the rectangle based on the function. There's actually a pretty simple way of thinking about what we're doing when we're doing that, and the way is the following. So suppose b minus a is small. Okay, suppose it's really small. So say a is equal to 1.0, b is equal to a plus 0. Alright, pretty small. And then I apologize for not being able to draw. It's pretty hard to draw when you're doing these things. So I'm just going to describe it and try to picture it as best as you can. You know what? That's not going to work for most of you though. So unless our minds are weirdly in sync. probably better if you have a picture to look at. All right, that's actually a nice picture. So you split the interval into small intervals, but suppose the interval is already pretty small, so you don't need to split it. And then the height of the rectangle that you put there is going to be the value of the function somewhere in the interval. So another way of saying that is that you just do something that will work perfectly for a function which is constant on a small interval. So if the function was exactly like that, right, boom, and then boom. If the function was basically the contour of these white rectangles, these green rectangles, sorry, then this method of approximating the function by a line would work perfectly. All right. So in first approximation, we can say if the interval is small enough, the function is constant over that interval. So for instance, we can say interval equals f of a times b minus a. All right, that's a rectangle. You have the length of the side times the length of the base or whatever, and that gives you the area of the rectangle, and that's what we're doing here. All right. Another way of doing that is going back to our analytical methods, and okay, so you have the interval, which let's write it like that. All right, f of x dx. Right, if f of x is constant, then let's write it like that. There isn't really any good way for me to write it at this point. But this is supposed to be this thing. A would be 0, b would be 1, f of x would be square root of x. That's this way I'm writing it right now, because I don't have the right symbols to write it. So if f is a constant, it comes out, for example, f of a, right? And then you do the integral of the constant 1, which is f of a times b minus a. And that's what we have here. All right? That's what's going on. Let's see if that's working. Always a good idea. I don't know why I wrote interval, but So for this exercise, we probably should figure out what the integral is, because otherwise we won't know if we're getting close or not. So the integral of this will be 1.0 over 4.0 times x times x times x times x minus x. And f of b minus f of a. And we need new lines. And now it's just too small to tell, right? So let's come back on our assumption. So now we see the real answer and the answer we get by assuming that the function is constant. But there's a problem with this. So before we go on, let's use double precision. Double precision isn't actually twice as precise. It's much more than twice as precise. In a certain sense, by using double, we're distancing ourselves from the problems that could occur with using numbers in computers. Okay. So the basic idea of assuming that the function is constant and then doing the integral can be extended a little bit. It seems like a dumb idea, but you can actually take it pretty far. But let's just take it a little further. And let's take our interval, which is no longer that small. Let's split it into 1,000 different intervals. And then let's do the integral on each interval separately and then add the whole thing together at the end. So before int I